So the original problem as written in this video is not solvable using the methods of our course. So over the course of this video, you'll see me change the problem a couple of times. And this one, the one that's shown on the screen right now, is the one we eventually end up succeeding in solving. 3y to the fifth minus 4y to the fourth minus 26y to the third is equal to y to the fifth minus 10y to the third. Focus on the processes and the steps and the cues in how to know when to do what process in this video. This doesn't look like a factoring problem when I first write it up here on the board, because all it tells us to do is to solve this equation for y. And the equation is 3y to the fifth plus 6y to the fourth plus 6y to the third is equal to y to the fifth minus 10y to the third. So there's a lot going on in this equation, a lot of different powers of y. We've got stuff going on both sides of the equal sign, and yet the task is still the same. Solve this for y. Find out what values of y make the two sides of this equation balance. And because we're at the end of a factoring unit, you can expect there will be some factoring involved. But again, the goal for today is to figure out how all the different methods of factoring work together with one another, and then also to get a reminder of how factoring fits into our broader strategy of solving equations. So I want to give you just a few minutes to work on this on your own first and see where you can get with it. Then I'll have you connect with a partner and see if you can make some further headway. Just tell me what you did first in this problem. You're confronted with an equation, and you're supposed to solve this equation for y, but it has all this stuff going on both sides of the equal sign. What was your first thought, your first priority, or your first step? So first instinct when looking at this equation is you're seeing some terms that are like terms to one another. In fact, what are they? What like terms did you find?
Y to the fifth with 3y to the fifth.
So there's a set of like terms.
And 6y, 6y to the third and negative 10y to the third.
Yeah. So there is a set of two pairs of like terms, right? The like terms that have the fifth power of y and the like terms that have the third power of y. And if we can, we want to get those together so that we can combine them. Our original equation has 5 different terms in it, 3 on the left side of the equal sign, 2 on the right. If we could combine them from 5 into 3, we'd be making some progress. So then my question is, how do we combine those like terms, given that the pairs of like terms are on opposite sides of the equal sign? What should we do? Add what and how? Yeah. So to collect these like terms, what I want to do is the way I usually think of it as a mathematician, I like to think of it as moving the terms from one side of the equal sign to the other. And how I move the negative 10y to the third, for example, is to move negative 10y to the third from the right to the left, I should add 10y to the third to both sides. Because then on the right-hand side, that's going to cancel with the negative 10 and give me no more y to the thirds. And on the left-hand side, that can combine with the like term plus 6y cubed and give me, how many y to the thirds do I end up with on the left-hand side? 16. So then on the left-hand side, I'll have 16y to the third. Okay? And so that takes care of how to take care of the 10y to the third. What else do I do to get the y to the fifth terms together? I'm going to have to subtract it, because on the right-hand side it appears with a positive coefficient. If I want to kill it from the right-hand side, I should subtract y to the fifth. And 3y to the fifth minus y to the fifth gives me 2y to the fifth. Great. And then my 6y to the fourth in the middle here remains as it is. And what do I end up with on the right-hand side? 0. And that is super, super important. Cannot overstate the importance of having that 0 on the right. Because it's not just about combining like terms, although that's definitely a bonus. It's mostly about making it so that one side of the equation is 0. So one side of the equation is equal to 0. Because when one side of the equation is 0, that is when factoring is useful, and not before. Right? Only when one side of the equation is equal to 0 is it even a good idea to think about factoring. Don't let factoring even cross your mind in an equation problem until one side of that equation is equal to 0. That's the tell. Having that 0 on one side of the equation is the indicator, it's the cue, that now is a good time to think about factoring. So I'm going to extra sort of highlight that 0 over here. That 0 is what we need to see. because now it's time to think about factoring. That way, we're only having to factor, first of all, one polynomial in this problem, just the polynomial on the left-hand side of the equal sign, as opposed to trying to factor the one on the left in the original problem and the one on the right in the original problem, and then trying to do something with both of those factorizations at once. No. If we wait until after there's 0 on one side, then we're only factoring a single thing, which is always a good idea. So that leaves the question, how do we factor 2y to the fifth plus 6y to the fourth plus 16y to the third? Because that feels like a process now. What was the first step in that process for you? The first step in your factoring process should always be to look for and factor out the greatest common factor of all terms. Look and factor the GCF of all terms. Because there are situations like this one where that greatest common factor is non-trivial, and factoring it out will turn a challenging factoring problem into a slightly less challenging factoring problem. What greatest common factor do you see between 2y to the fifth, 6y to the fourth, and 16y to the third? So each of the coefficients, 2, 6, and 16, all have a factor of 2 that we can bring out. So that'll get us started. What else do all of these terms have in common that we can factor out in the GCF? How many factors of y? Y to the third. Again, when we factor out the greatest common factor of a set of monomials that all have the same variable, so they're all powers of y, like in this example, the factor with the smallest exponent, we know, will go into all of them. So y to the third, because it has the smallest exponent, it goes into 16y to the third, it also goes into 6y to the fourth, it also goes into 2y to the fifth. And so the greatest common factor that I can bring out is 2y to the third. So then the question is, if I bring 2y to the third out, what's in? What is its cofactor that makes up the expression 2y to the fifth plus 6y to the fourth plus 16y to the third? What lives in the parentheses here? Y squared, because that's what separates 2y to the third from 2y to the fifth. Again, when you multiply powers, you add exponents. And then what separates it from 6y to the fourth is a 3y, and what separates it from 16y to the third is an 8. And my right-hand side of the equation is still 0. Great. So that was our first factoring step. Look for and bring out the greatest common factor of all the terms. Cool. Okay, then what? Just for the moment, if we were going to factor y squared plus 3y plus 8, it would require us to find a pair of numbers which multiply together to give me 8, and at the same time add together to give me 3. Now, no matter how hard you try among the whole numbers, among the integers, you're never going to find a pair that works. 8 and 1 don't work, neither do their opposites. 4 and 2 don't work, and neither do their opposites. Right? So we are stuck in this example. This green expression is not one that we can factor, at least not over the integers. So what I can say about it for now is that we will learn how to handle this later in the course. So not probably either next week or the week after. We can handle this in Module 10. But this is an example that we can't handle right now. So I've gone back and I've changed the original problem so that it reads 3y to the fifth minus 4y to the fourth plus 6y to the third on the left-hand side. That's a luxury that I get as a professor, and you don't get as a student. Unfortunately, you can't just go back and change the problem if you don't like it, but I can because I'm making a point. So if I change that to a -4, then how do I change this factoring step here? What should I have in my middle term of the cofactor? Y squared minus 2y. Yeah, so that would be a change to what we had before. And now that it's y squared minus 2y plus 8, how do I factor this quantity in green? Yeah, I'm going to use that sum and product trinomial trick for trinomials, where it applies. And we can get away with that, again, because this particular trinomial has a leading coefficient of 1. Right? There's no extra coefficient in front of my y squared, so I don't need to use the technique we talked about last time, the method of the a's and the c's. So we'll just use the sum and the product technique, which tells me that if I can find a pair of numbers which multiply together to give me 8 and which also add together to give me -2, then I'll be in business. And among the paired factors of 8, the pair that has the most promise here is a 4 and a 2. Because then we can arrange the signs on that 4 and the 2 so that their sum is -2. So which of the two should get the negative sign, the 4 or the 2? If their sum needs to be -2, right, the 4 should be negative. So -4 and +2 wins the sum and the product game for this factorization. So that means that what I'll end up with in the parentheses is a y minus 4 and a y plus 2. And I still have 2y to the third sitting in the front. And I still have an equals 0 at the end of the line. Sometimes people get so wrapped up in solving and factoring in these problems that they forget that there's an equal sign on the right-hand side to the equation. Don't forget it. If it's on the line above, make sure it makes it to the line below. Right? Make sure every single piece of everything you copy down survives the copying process. Because now I have an equation with a 0 on the right-hand side whose left-hand side is completely factored. So what does that allow me to do? This is the step that too many people forget. After you go through all the trouble of factoring, what can we do now that we couldn't do before? We want to solve for y. And in order to solve for y, how do I use those three factors? What we want is we want to split. Split each factor into its own equation, which is a way of sort of dividing by each factor that avoids the eventuality that that factor might be 0, and hence we are not able to divide by it. Splitting the equation so that each of its factors gets its own simpler equation, 2y to the third equals 0, y minus 4 equals 0, and y plus 2 equals 0, considers the contribution that each of those three factors makes to the zeroness of the left-hand side of this equation separately. But since each of those factors is much simpler than their product was, now we have, instead of one complicated equation to solve, three somewhat simpler equations to solve. So yeah, we have a problem with the plus 8 in this equation. What we really wanted was a minus 8, so I'm going to again indulgently change the problem so that we have a minus there, which means that I would need a minus here, which means that maybe let's make the original problem minus 26. So now I've really munged up the original problem into something that doesn't look much like the original problem, but at least now, when we run our factorization, we still end up in the same spot. So if you're watching this discussion video later on, you might want to start at the end to see what the actual equation was that we solved, so that now all the steps hopefully make sense in retrospect. Thank you for the correction. So now all we have to do is solve each one of these equations in isolation, two of which are pretty simple to solve. Add 4 to both sides of this equation to get one solution, y equals 4. Likewise with the equation on the right, subtract 2 from both sides to get another solution, y equals -2. And then lastly, we have this equation over here, 2y to the third is equal to 0. What should we do with that one? Well, I'd recommend dividing by 2 first of all. Following the reverse order of operations, we have multiplication and an exponent going on in here. If I'm trying to unwrap the y, I should undo those in the opposite order. First dividing by 2 on both sides to get y to the third is equal to 0 divided by 2, which is 0. And then asking the question, if y to the third power is equal to 0, what does that tell me about y? What number yields 0 when we multiply it by itself 3 times? What's the only number that gives me 0 when I multiply it by itself 3 times? 0. Yeah. Another way to think about it is we could split this equation, because on the left-hand side, y to the third is really y times y times y. I could in turn split that equation into 3 equations, each of which reads y equals 0, y equals 0, y equals 0. Right? So whichever way you slice it, that first equation gives us the solution y equals 0, which, by the way, is exactly the solution we would have missed if we chose to divide by 2y to the third. We would have missed out on it. But there's a lot of steps in this process, and really, to me, for today, for us, the process is the most important part. That if I'm trying to solve a polynomial equation for its variable, the first priority that I have should be to make one side of that equation equal to 0. Before that happens, you shouldn't even think about doing anything fancy like factoring. Right? Focus first on getting all the terms to one side and collecting the like terms together, so that one side of the equation becomes 0. And only then should we think about factoring. And when we think about factoring, the first priority is always look for the greatest common factor and factor it out first. Look across all the terms that you have and ask, what do they all have in common? Factor that out, and then once that's been factored out, if we have a trinomial, like y squared minus 2y minus 8, then we can think about the techniques that we know for trinomials. The sum and the product trick in this example, because the leading coefficient was 1, or if the leading coefficient had been something else, like if this were 5y squared minus 2y minus 8, then we would need to think about the A and C method that we talked about last time. But here it was a coefficient of 1, so we could just get away with the sum and the product. And then after all of that factoring is done, then comes the step again that people struggle to remember in the heat of the moment. After you win the factoring process, split each of those factors into its own simpler equation with its own equal sign and its own 0. That's going to give you, in this example, 3 simple equations to solve instead of one complicated one. And at the end of this process, what we come away with is actually 3 different solutions to our original equation. Y equals 0, y equals 4, and y equals -2.